I used to deliver the lecture for how many weeks? 16 weeks, 3 hours a week. But now I reduced down to about 6 weeks. So it's very short duration to deliver the similar, not exactly the same amount, the similar amount of the information that I really want to talk. So I'm going to accelerate a little bit. After chapter 2, it's much easier. Chapter 2 takes a little bit time, and I didn't give you any homeworks, things like that. But after chapter 2, I'll start giving you not really many different problem set, but the set I feel is important to know. That's what I'm going to do, okay? This here is T is duration of the gas bubble. So duration of the gas bubble is, when I say duration, this is really first duration. So the gas bubble expanded and down to the min is a 1 period. So this is really initial gas bubble period is what this T is. But this is all unit dependent. And here, this parameter, the 4.268, this is really the explosive dependent parameter. In this case, this is good for TNT. As you will see in chapter 3, I depict a few explosive and give you all different parameters for that, okay? This is atmosphere, this is 33 feet is hydrostatic, the depth, which is equivalent to atmospheric pressure, okay? But this is really a US gravitational unit, so that's what you have to think. But you can convert into metric, but when you convert into metric, you have to be careful on this parameter. So not just to convert D or W, so you have to pay attention on that. But the European people, they already converted in metric, so they are using it. So I think Dr. Kim, you already maybe converted, or you have converted, right? No? But you can use as is. T is a second, D is in feet, W is pound force. It's a pound force, okay, not the pound mass. So as you see here, 14.7 psi is a pound force per square inches. And if you're gonna, I convert into the pound per the feet square. So you have to multiply 144 because 1 foot is 12 inches. Then this is equivalent, D is hydrostatic depth times 62.4 is mass density of the water. So 62.4 pound per cubic feet, okay? That's what the mass, the weight density of the water, and multiplied by hydrostatic depth. D is what the unknown to find, then is roughly 33 feet. So that's where the 33 come into picture. And 5/6, this is all the result determined by experimental data. A couple pages before, you see that the T is proportional to like 5/6. If you turn back the couple pages downward direction is there. So, if you know the charge depth and the charge size, you can determine initial gas bubble, the oscillation period. So if you compute the capital T, then you can compute the fundamental frequency of gas bubble motion, which is 1 over T is equal to F, okay? And R is concerned, the radius of gas bubble is initial size of gas bubble, not the second gas bubble. Second gas bubble size will be smaller than initial gas bubble because energy dissipate into the water as the bubble expand and contract in that process. So here is again parameter for T and T to compute the radius, and W and D is the charge depth. So it's very clear. If it's not clear, let me know. And this is a gas bubble. The motion, horizontal axis is time, and this is gas globe, just the gas bubble size. And as time goes by, the gas bubble radius is increasing and down to the minimum, then bubble collapses. Then at the meantime, as I said, the energy is keep released into the water. So next gas bubble size is smaller than first, and third is smaller than second, so on. And this is a gas bubble migration path, which really means the center of the gas bubble, as time changes, will go slowly up and up. So this is a direction, you know. So here it keep coming up. Then when the gas bubble is really minimum here, that gas bubble really move, it's all vertical motions, okay? But gas bubble is not going this way. Gas bubble is migrate toward the free surface, but when you expand the show in the time domain, then of course that's the way it can draw. So gas bubble really after the collapses, gas bubble shooting up faster than any other time here, shoot up, then almost linearly going up. Then after gas bubble collapses, it migrates very fast. Question arises before, as I mentioned, when I give a talk in the electric boat in Groton, where they built the submarine. One student, engineer, said, how come gas bubble migrate faster? Because he said it should not be faster because gas bubble size is really small. Then drag force, which is called the hydrodynamic effect. Drag force should be very small, but the buoyancy force is, of course, is small. And how come that shoot up so fast? So that kind of the question. So I'm going to explain in the next couple of pages why gas bubble migrate fast. Okay. Then here is incident shock wave pressure. Okay, at the beginning. Then gas bubble is getting larger. Then pressure is just this is as I mentioned, just 2 to 3 or 3 or 4 psi is not meaningful. You can set in the computation always 0 as a dynamic pressure. And the first gas bubble pulse, which means as it bubble collapses, then whenever something collapses, a secondary explosion occurs, or called simply the bubble pulse. And another bubble pulse here. At the same time, gas bubble migrate toward the free surface, okay? So depend on the charge depth. If it's very shallow depth, there may not have a second gas bubble, maybe only one gas bubble. If the depth of the charge is really deep, then you could have a third and fourth the gas bubble pulse. But usually, you know, it's really few hundred deep, maybe 3 or 4, that's about it, okay?
Question.
Yeah.
So when I see this picture, between pressure and the first stage is the pressure indicates zero. Below the zero. What does this mean?
Okay, why below the zero? Anybody can tell why? Hyun-Chol has a good question. Why this goes below the zero? I talked a little bit Monday. Strictly speaking, the water can resist on the tension, okay? So, but which is very small, the pressure, it can resist. So that's another way of explaining. Another thing is, I didn't just, chapter 1 is the introduction portion, and this, okay, this depends on how you define the pressure. I can define the pressure as a dynamic pressure. Dynamic pressure, okay? And which means the total pressure take away the hydrostatic pressure. So that could be in there, but I didn't say anything, it's just a shape is, this is really due to the ability of the water which can resist on the tension. So, so this portion is resisting like a pressure, okay? So not much meaning in here, but as you go into chapter 3, then I have to consider real hydrostatic pressures, tension wave pressures and all that, then you have to really pay attention. But here is just a general. Chapter 1 is just the introduction. So this is why very small pressure, okay? Yeah.
Is this pressure inside the bubble or?
Oh, this is, you can say the bubble surface. Okay, it keeps changing it, bubble surface. That's a very good question. And as you see here, when the bubble collapses, originally you could imagine the spherical shape. And when the bubble gets down to the minimum, then now it loses the stability, which means simply you can think of top of the gas bubble and below the gas bubble there's a pressure differences. Below here, below the gas bubble, the pressure is higher, right? Simply speaking, hydrostatic pressure then has a tendency to move the pressure from down to upward direction. So I put this in, then start losing the shape, spherical shape. Then once it's distorting, then loses original shape, then bubble collapses. Bubble collapses, but it's all surrounded by the water. Doesn't go anywhere. Like air explosion, then it goes up, then collapses, some bubble pulse occurs. This is small, the gas bubble collapse pressure. However, as I mentioned before, this area or volume in terms of the 3D, this volume is small. Area under pressure is small. But still, compared to this impulse could be larger. But here is a pressure, peak pressure is very high. So things like that. Good question. Okay, this is the supplement which, after I came back from lecturing the whole day, why the gas bubble velocity at the time of collapse is just shooting up faster. So this is what the simple calculation is, but this is showing by using this you can explain nicely. Linear impulse is change in momentum. So that's the equations I use to verify or to prove why it's going up faster. First, for the gas bubble, assume, of course, it's really spherical shape. The buoyant force on the gas sphere F this is a displaced mass of the water, right? So which is 4/3 pi A. A is radius of gas bubble. Q is a volume. Volume of the gas bubble times rho is mass density. It's really mass of the displaced water of that volume times G, okay? So that's what the buoyant force is, pushing upward direction, buoyant force. And why do you need this? The area of buoyant force, that's external force. This is what the linear impulse is. So next, to compute the vertical momentum of a gas sphere acquired by the water at the time t. This is ma. We used to call the added mass effect, added mass, or hydrodynamic mass, which means gas sphere is in motion, vertical motion in the water, and as a result of the viscosity, there is a drag force formed surrounding the gas sphere, which is dependent on the shape of the bubble. In this case, assume the sphere, so which is 2/3 pi A cubed, then multiplied by the mass density of the water times U. Okay, that's what the momentum, vertical momentum is. Added mass times the U. U is the velocity of the gas sphere. So vertical bubble velocity. Then you apply the linear impulse is change in momentum. So here is a linear impulse. This is at time t minus moments at time 0. At the beginning, everything is all 0 for the momentum wise. Then I can say this reduced down to this. Then you just plug in the force, the buoyant force, and mt. Then you have the final equation set. As you look at the final equation set, then I express this for u. U is minus dz over dt, minus u is going up. Originally set the z, positive z-axis as a downward direction. I can put the minus. Depend on if you're going to put the positive z upward direction, that's going to be positive. Then So minus dz over dt is from these equations. So you can just put it, this is integration from 0 to time t. The t, the moments you are considering. So this is one, the fixed value at time t. So u is constant, this is a constant, this is constant, right at time t. A is radius cube, so u is proportional to 1 over a cube. When a is small, this value goes up. So that's what simple, of course there could have more factors to consider the bubble, the vertical bubble speed. This tells you when a is small, bubble goes up fast. Very good justification and very simple. The linear impulse is change in momentum. Okay, the few words on the wave. There are a lot of nomenclature or type of the wave you are considering sometimes are confusing. Surface cutoff occurs due to the tension wave, and the bottom reflection, which bottom reflection is a compressive wave, and refraction wave is compression wave. Spray dome caused by the shock wave, or the first plume caused by the first bubble pulse, and second plume caused by the second bubble pulse. But here, this explains nicely here. As I mentioned Monday, this is called the incident shock wave path as it propagates. So when explosion occurs, the first wave which will hit the target goes straight along here. Incident shock wave. This is compressive wave. I put the plus for compressive wave. But here, the first, wave which will hit first to the target as a reflection wave. So here, wave from here all the way to down to the free surface, this is a compressive wave. From here, the reflection occurs, so I put the image charge way up there, which is symmetric about the free surface, like a mirror image here. Then coming down, you can draw the line here. So reflection wave is concerned, this is coming up to here is a compressive wave. From here down here is tension wave. In explosion computation, you have to really know this is a negative wave, tension wave. Acoustic wave or shock wave propagate after reflection, it comes down toward the target. Okay? Wave is coming down toward the target. However, the fluid particle is moving toward the image charge. Fluid particle is moving toward the image charge, but the acoustic or shock wave is keep coming down toward the target. That's called the tension wave or rarefaction wave or surface reflection wave. So that is always the same. So rarefaction wave, in the past there was some confusion among the students, but it's all same. Rarefaction wave or tension wave. Tension wave. and the surface reflection wave is all same. Okay? If I draw the time versus the pressure, okay, tension wave occurs after the incident shock wave, so I can draw simply in negative. This is a minus, this is a minus P. And for the incident shock wave, it could be like, I'm going to draw up to here. So this is like a total pressure. I don't write the whole thing yet, because in a minute I'm going to show you all the wave right here. So this is a P atmospheric pressure. Let's say PA. Okay, incident wave include, right? So this is a kind of the P naught I use, or P max dynamic pressure. So here is the total. This is a P max is a total pressure. And this guy here is a P, I'm going to just write as a negative, which means due to the tension wave. Okay, now I'm going to add this guy, P max, plus P negative. Okay, if you add these two together, if the resultant pressure comes around here, what does it mean? Target receive the compressive pressure. But if you add this guy to that guy, if it comes down here, Joel and Yonggyun missed this class, which is really not good. Basic concept. If it reached down here, what happened? This is a negative pressure. But water, basically, even if it can sustain the tension a little bit, that's really a fraction of the 1 psi, very small. You can assume that that's equal to 0. If it comes down here, if the resultant, then you have to reset to 0, because you can assume freely water cannot sustain the tension. Even if the physicist wants to identify even 0.3, 0.4 psi, when we are dealing about 100 psi, 1000 psi dynamic pressure, so you can reset to 0, okay? When it comes down just before, you can assume this is equal to 0. Got it? It's so small. So that portion is important. This is a tension wave or rarefaction wave. So pressure along here is a negative pressure path over here. All others is a positive. This is a reflection wave. And here is a compressive wave. After it bounces, to do that, to draw the path of the reflection wave, you have to put the image charge about this guy. You draw the line to the target. So then you can determine that point. Then it's going to come down and shoot up. That's the first wave reflect and hit the target. And this is a compressive wave, bottom reflection wave. What about this? What do you call this wave? This you can make up. What do you call it? Just hit it. It transmits into the soil and goes around and come back right out there. Such a wave is called the transmitted wave. It transmits into the soil, then back out. Okay? Or refraction wave. So which is called the transmitted wave, or refraction, A-C-T-I-O-N, refraction wave, okay? Not the reflection wave, FL, reflection, surface reflection wave is what this wave is, surface reflection wave.
Professor, which
Yeah.
wave can do the critical damage to target?
Incident shock wave and also tension wave.
I don't know exactly between tension and compression wave difference.
Difference?
Yeah.
Pressure is compression wave, pressure is hitting. And the tension wave is concerned when it comes down here, it reduces the pressure. So just to wait maybe another few minutes, then when I put all the wave together, so like this, okay? Like this, for example, if it comes down here, you can add these two together. If you add these two together, what happens is, I'm going to simply add it together. It's going to go like this, because nothing here. Then coming down here, then what happened? As the surface cut off, cuts like this. Maybe here, it could come back down here, then could go up mathematically. But water cannot sustain the tension, so it's going to come down to zero, then it's going to go flatly like that. So tension wave, because of the existence of the free surface, tension wave reduce down the incident shock wave. But the incident shock wave hit the target, then moving away. And the tail end is there. This is a tail end. But for the tension wave is coming down here, this is not the same amount as this guy. This is this portion is smaller, the peak. Because why? Because if you look at the distance, if you look at the distance from here, and here, total the distance, the shock wave travel is longer than this guy. So amount of the peak pressure is smaller. So in other words, if I just put the mirror image here, image charge, I can just connect this to this. This total length is same as this plus that. That's longer than this. So total pressure hit by the tension wave is smaller, which means this is smaller than this. So anyway, when you add the two together, so it's going to come down here. So physics say, no, you can't do that, because water cannot sustain the tension, then come down, and surface cut off phenomena occurs, then it's getting into the zero. Nothing is difficult. This is beginning, but the wave action, this is the wave action you have to really understand too. And this is so-called the spray dome. So, spray dome not showing here. Spray dome is some, I think you saw the movie, the DDG-81 Shipshock Trier movie. As you watch carefully, you could remember at the time of explosion, as you look at the surface, it's kind of the parabola type of the surface. Is from the flat, it just goes up right after explosion. That's what the spray dome is. Okay, this is due to what wave? This is due to what wave? Caused by what wave? Shock wave, not the bubble. Due to the shock wave. Shock wave is moving something like 8,000 meters per second at the beginning and converge into about 1,500 meters per second. Okay, so spray dome. And next you see the white gas bubble. This is due to what? This is due to the first gas bubble, the pulse. It's all lifting up the water particle upward direction, and is all moving the gas particle upward direction. Then bang, the first gas bubble collapses. It generates the shock. So it's all white because it's just disturbing the water particle motion, and all white here. And as it then the fluid particle, water particle is all shooting up, right? Then second gas bubble pulse occurs. As it first gas bubble will really put the water particle going up, then it will come down. Then second gas bubble pulse occurs. Then as it comes down, and due to the second gas bubble, water particle is shooting up. It's a whole mass, still white color. No other color, white. It's due to the wave action. Then, after that, as the second gas, it's called the plume. Plume is all the water particle motion. Then suddenly the black stuff is coming from the right at the water surface, is coming right up. That's a venting occurs. It's now everything is shooting up. The black stuff is really all the ashes of TNT. After explosion, all the ashes comes straight up, then finishes up the explosion process. Remember that. Black stuff. You saw the DDG-81 Shipshock Trier. Otherwise, you can borrow from Higyu, rerun that area. When the black stuff comes up, it concludes the explosion process. Okay, any question? Any question? Yeah.
So, the three picture, all those indicate the same position?
Same position. Same position. One is a spray dome. It's just forming up. Same position. Okay, the explosion occurs below, right? Same spray dome due to the shock wave, right? But it's not after the 1 second. No, it's instantly processing all together, right? So then once you see the spray dome, then it's just a continuous explosion shooting up. Then you will see that that's sort of the small, well, not depend on, then white plume. Then it's gonna picking up some more because it's already going up. then second gas bubble motion is shooting up, and as it coming down, it's a whole mess. Then all the black stuff coming up due to the TNT ashes, all the ashes, that just it's called the venting process. So it's all venting out, then finishes up. That's what. This is late 1980s. I use first generation of Macintosh, small box, and I drew all that by hand, and it was good. Any other question? You know, this process is, you've got to know the process. It's a sequence of explosions. That's about all. What happens if explosion occurs way in the deep? What happens? You're going to have a spray dome here. It's called a spray dome. Spray dome. It's really beautiful shape. You saw it in the video, the motion, video clip. And at the deep, then you see the spray dome, possibly yes. When you're dealing with a 10,000 pound TNT explosion, which has been used widely for ship shock trier. You see that? And of course, a ship shock trier, you see that. If it's deeper with a smaller charge, you may not see a clear spray domes or things like that, because all the hydrostatic pressures and just compresses down, and the bubble may not be able to escape the free surface. Very interesting. Is it interesting? Interesting. 현철, interesting.
Yeah, but very difficult.
Very difficult. But you can compute without introducing the structure. You can compute all this fluid particle velocity. You can compute the plume motion. Because we can compute in the next chapter, you can compute the fluid particle motions. That's what that is. P is equal to basic, simple equation you will learn to drive is P is equal to rho C U or V. This is a function of time t. This is the mass density of the fluid. This is acoustic velocity of the fluid. Or you can say this is 1500 meter per second, and this is a shock wave of pressure. This is a fluid particle velocity. That's what next chapter I'm going to reintroduce the conservation law. You all knows the conservation law. You can't deny I never saw the conservation law. Using the conservation law, then I will drive for such a important equation. It's really important equation for the shock calculation. If you don't know, you cannot do anything. P is equal to rho Cu. This is good for the plane wave equation. And like a near field explosion, you have to deal the shock wave as a spherical wave. Then you have one additional term, which is the function of the shock pressure history plus the distance, stand of distance, which is the distance from the explosive charge to the target, okay? So which means when the stand of distance is really long, that's approach to 0, because the secondary term is 1 over rho c naught integration of the p. So r term is there, r squared term is there. Rho c naught r squared. This is a stand of distance is proportional to the inverse. Pressure is inverse, proportional to the inverse of the stand of distance square. So if it's long, it's a square. 1 over the distance is square. It's getting small. When the distance is really far away for the target, then curvature effect is 0, almost 0. See, curvature effect. But if it's a near-field explosion like a Cheonan naval ship, it's too close. Curvature effect is tremendous. Second term effect is tremendous. But for the far-field explosion, which is R is very long, okay, even if you put the charge of 10,000 pound charge, when it let it happen, 1 over r squared term is almost 0. What that means here, you have a surface ship. You have a surface ship, then now it's similar to the wave, which comes as a plane wave, one-dimensional wave. So idea is, for the ship shock trier, idea is to excite the ship with a plane wave, hit it all together from the bow to the, what do you call, this is a bow, then this is called? 이거 한국말로 뭐라 그래? You have this tip, 뭐라 그래? 갑자기 생각이 안 나네. It's 한국말로 뭐라 그러지? 이건 수미, 이거는 응? 선수, 이거는 선미. 선수 선미를 try to put the plane wave, one-dimensional wave, excite the whole ship with the same pressure profile, because interest is there is to really see whether equipments will survive or not. I don't want to just apply the spherical, the shock wave, which will excite harder at the center than reduce, which you don't want that. Yeah, okay. Any other questions? Okay. Okay, this, again, as you will see, the way I give a lecture is repeat the same thing over and over again, then reminding a couple of times, a third times, then you will feel too much. Okay, then we stop, okay? So that's what we're going to do then. And this morning, you know about OMAE conference? You should know, which is offshore platform types, subsea and all that stuff. Maybe Sangtae should know. OMAE? No?
Yes, I heard about it.
You heard about it. So I proposed them. They are still asking abstract. I wrote a quick email. I proposed that I can give a talk for an hour or two on the underwater explosion and its effect. They need also explosion in the deep ocean. Okay, this is done in chapter 1. Chapter 2.1 is done. And Friday I'm going to do the 2.2. If I'm lucky enough, I can finish the 2.2 on Friday. So I don't have much time. I look at the schedule. I have a 10-hour to talk to cover the whole thing. So I'll do my best to do that. And I think 17th of December is a Monday, as I look at last night. So, which means the last final lecture will be Friday, December 15. That's what I see it. So December 15, I have a 10-hour to give a lecture counting from Monday. And also, I might have to give you another hour in addition to 10 hour, and at least one exam for underwater exploration area. So that's what, and a few homework problem that you can solve. Okay. Any other questions? If it's not clear for any part, just come to my office, then I can explain additional things, okay? Abdullah, same thing. Okay, I am getting better. Monday was really bad. Now it's a Wednesday, feel much better. 17 hours change in 1 week is disaster. Go out there and then slowly adjust it for a week. Then coming back out here, then 17 hours adjusting. It's kind of tough, but now, this morning I feel much better. So, what happened to Yesul, Joel, Youngkyun? I know Bongshik has a single disease. I hope he recovers well. That's about it, right? Bongshik, Youngkyun, Joel, and Yesul. Yesul was here the other day. But, okay, I'll see you Friday morning at 10 o'clock. See you.